Welcome to Calculus One. I'm glad you're in this course, or maybe quest, for understanding calculus.
And that raises a question, what are functions? If we're going to be studying functions, we should know what they are. And that question's pretty metaphysical. I mean, what are numbers? What's the number for? So a function takes some input and produces some output. That's what it does. But how is that supposed to make us feel? You know? How are we supposed to imagine that? And I've got this number 5 here. And I'll start the conveyor belt going, so the number 5 starts moving through the machine. And when the machine is done processing it, it comes out from the other side, and now it's the number 30. Right? The distinction between local and global maximums is really quite important, even in everyday life. When you're standing at a local maximum on the top of this mountain, small changes to your situation just make things worse. And yet, if you're willing to go through this valley, you'll eventually come up here to what at least appears to be the global maximum of this function.
I want to say a little bit about how this course as a whole is structured. Right, we're really covering 3 topics. We're covering limits, derivatives, and integrals.
Right? This quantity is measuring the profit on an investment of X dollars in widget production. We need some framework, some general picture that lets us understand how one thing changing affects something else and how that thing's changing goes on to affect something else. So let's think about this chain rule. The derivative of g of f of x. You can see this pictorially as well. You can see that for an input change to x of some small amount h, the output changes by about g prime f of x times f prime of x as much, which is exactly what the chain rule is telling me should be the case. Sense that this is the correct rule, that the chain rule really is the derivative of the outside at the inside times the derivative of the inside function. Suppose that we have some sort of substance, I'll call it gray goo, that converts anything it touches into more of itself. The rate of growth of this gray goo is proportional to its current size. Well, let's say that the constant of proportionality is just 1. For 10 seconds, there's about 22 kilograms of gray goo. Okay, here's the big question. How long will it take until the entire Earth is converted into gray goo? You've got, what, 64 seconds. In other words, you have no chance to survive. Make your time. I'm going to blow up this balloon. In particular, a really big balloon doesn't get a whole lot bigger for a given change in volume compared to a little tiny balloon, which gets quite a bit bigger for the same change in volume.
We're often trying to pick the best of something. We're trying to optimize our lives, right? We're given a bunch of choices and we've got to make the best choice. But how do we do this? And it turns out that calculus comes into play. We can use calculus to solve these kinds of optimization problems.
The calculations that we're doing here are just symbols on the page, and yet somehow they manage to govern the real physical world, right? This ladder's not long enough yet to get you all the way to the barn. At this point, you're probably feeling really bad. You now recognize that this is an optimization problem, but you're thinking, oh no, not again, not another optimization problem. I've drawn some region in here with 3 edges. If this is y, I can solve this equation and find out that in that case x is y squared. So y goes from 0 to 1,
and this integral calculates the area of that region. So the area of that shark fin-shaped region is 1/3 of a square unit. Often, it's not that there are right ways and wrong ways, but there are better ways and worse ways, right? Ways that are better in that they're quicker, safer, and more elegant. So don't just make good choices, make the best choices. So let's move up a dimension and think about volume. Let me ask really loudly, what is volume? And let's take that region and rotate it around the x-axis. When I take a region in the plane and rotate it around an axis, I get a solid of revolution. And the question is, what's the volume of that solid? So this is the volume of just the washer, the part that remains, and I can write this maybe a little bit more reasonably as pi times big R squared minus little r squared times the thickness dx. Now I'll use that formula, the volume formula for a washer, to write down an integral that calculates the volume of the solid of revolution. And I want to add up the volumes of washers for x between 0 and 1. So my integral is going to go from x equals 0 to 1. Pi times 3/10. So that's the volume of the solid of revolution. And we did it.
Imagination is more important than knowledge.